plastic water bottle partially filled with water. Under certain conditions, the bottle is launched and flies into the air. Investigate how the acceleration during liftoff depends on relevant parameters. Here is a video demonstrating my experiments. Now, here are the parameters we think are responsible in this phenomenon. The mass of the bottle and the water, the bottle volume, the pumped pressure, the aerodynamics of the bottle, the nozzle area, and angle of launch. So, let's start with the preliminaries. As air is pumped into the bottle, internal pressure increases, exerting force on the water. Once this pressure exceeds atmospheric pressure, the water is expelled downwards, generating thrust according to Newton's third law. The thrust initially produces high acceleration. As water mass decreases, the thrust diminishes. When all water is expelled, no more thrust is produced. At this instant, the rocket reaches maximum velocity, but continues upwards due to inertia. As the rocket ascends, it deaccelerates under gravity until its velocity becomes zero. This is the maximum height. The rocket then undergoes freefall with downward acceleration equal to gravitational acceleration, assuming negligible air resistance at this stage. Here we can see the transition between the first and second phase of movements. In the rest of my presentation, I'll be analyzing only the first phase, according to the problem statements. So we can categorize the phenomenon into three main stages: air expansion, mass dissipation, and thrust force initiation, and diminishing factors like the turbulent flow, which I will discuss later. So, we're going to talk about the Bernoulli principle, which is an equation for determining the relation between pressure and velocity in a fluid. The assumptions of the Bernoulli principle are steady flow, incompressibility of the fluid, and negligible viscosity. Now, for water, incompressibility is a valid assumption. However, viscosity and flow stability must be considered. Viscosity introduces energy losses, and we're going to investigate whether the flow is steady or turbulent. So, we have Reynolds number, which is the dimensionless quantity used to predict fluid flow patterns, and it helps classify the nature of the flow. It is defined as the ratio of inertial forces to viscous forces in the fluid. Now, depending on the inputs of our experiments, we are going to calculate the Reynolds number. Based on the calculations, we can say that for velocities under 10th of a meter per second, the flow is steady, and for velocities above this number, the flow is turbulent. Based on my experimental data, the velocity of the water ejecting is much more than this, so we are not able to use Bernoulli's model as is. We will have to modify it to justify the expectation of the energy loss. Now, adiabatic processes in thermodynamics are processes that occur without any heat transfer. For our purposes, we consider the expansion of air as adiabatic. The rapid expansion happens too quickly for significant heat exchange. And using this assumption, we can employ the following formula. Now, this is the Bernoulli principle. Here are the terms of the principle. Now, okay, so here we have the Bernoulli principle. To estimate the exit velocity of water from the nozzle, we use Bernoulli's equation between a point in the pressurized region and a point just outside the nozzle. We simplify the equation by noting that the internal velocity of the water is very low due to the large volume, and we treat gravitational terms as insignificant given the small vertical gap. However, since real flow is turbulent and subject to friction, we introduce a subject coefficient to correct for deviations from the ideal velocity. We're going to show this coefficient as the coefficient of discharge. The thrust force exerted on the rocket is a consequence of momentum change as water is expelled from the bottle. In this case, we assume that the water exits uniformly and perpendicular to the nozzle area. The mass flow rate is proportional to the water density, exit velocity, and nozzle area. Since the thrust depends on the square of the exit velocity, any variation in internal pressure over time directly alters the thrust. We also account for the decrease in water mass by integrating the flow rate over time, which allows us to track how the mass of the rocket changes as water is expelled. We assume the process as iterative, as I mentioned before. The timescale of the launch is very short, about 10th of a second, so we feel that that assumption is valid. So heat transfer is minimal. We can say that PV to the power of gamma is constant. This lets us derive how the internal pressure evolves as the water volume increases. We apply Newton's second law. Acceleration equals net force divided by mass. Both the force and the mass here are changing continuously. As water shoots out of the bottle, the mass gets smaller, and the thrust, which comes from the pressure difference, also drops. We also have to consider two other factors: gravity, which always pulls down, and air resistance, which grows stronger as the rocket speeds up. Now, concerning bottle volume, we know that using different volumes of water can change the expansion ratio. A smaller bottle has a higher expansion ratio and a lower final pressure, but a larger bottle maintains larger internal pressure and higher thrust in water release and thus has higher acceleration. When launching the bottle at an angle, the thrust acts along the direction of launch, while gravity contributes a component opposing the motion based on the launch angle. Drag also acts opposite to the velocity vector, reducing net acceleration. To better understand the rocket's motion, we built a numerical simulation in Python. By solving the time-dependent equations for pressure, mass, velocity, and acceleration, we could model the launch in detail. This approach allowed us to account for changing parameters over time. Now, for my experimental setup, I used an air pump, a bottle holder, several bottles, a cork to secure the bottle, and a scale. The camera stand was positioned to minimize parallax and spatial error. In my setup, the angle of view was about 5 degrees. I feel like that is a good enough error. And here we can see a graph, which is the acceleration based on the mass of water. The curve is parabolic, suggesting a peak at about 200 grams, suggesting an optimal balance between available thrust and rocket mass. However, in these trials, pressure was not a controlled parameter, and the rocket launched with the pressure needed. So we created a method to actually stabilize this pressure. Now, here is our experimental method for controlling the internal pressure. We used plastic bands to secure the cork the video is not playing. Okay, I'll play the video later. To secure the cork, when cutting the band off, the rocket will launch in our desired pressure. We use Tracker, a video analysis tool, to determine the rocket's acceleration frame by frame. By tracking the position over time, we can extract reliable velocity acceleration data from the launch range. Now, for measuring the discharge coefficient, we use the formula for the volume of water exiting. And using this, we were able to find the average velocity of water exiting. We compared this to the results we got from our theoretical data, and we were able to determine a discharge coefficient for each initial velocity. However, we need to note that drag is highly dependent on velocity, so I actually determined the discharge coefficient based on internal pressure. So we have different discharge coefficients for different initial pressures. So now this graph shows these are my actual experimental results. This graph shows a clear linear relationship between internal pressure and acceleration. As expected from Newton's second law and our thrust model, increasing the pressure directly increases the force on the rocket, leading to greater accelerations. Here we see another linear relationship, this time between nozzle area and acceleration. A larger nozzle allows more water to exit faster, increasing thrust. This confers the model linking thrust to both pressure and nozzle area. In this setup with constant internal pressure, acceleration decreases as water mass increases. Unlike the uncontrolled trials, there is no peak here, just a steady drop. This suggests that while more water increases total thrust potential, the added weight and limited flow rate through the nozzle reduces the net acceleration. The trend highlights diminishing returns when increasing mass beyond what the system can efficiently expel. Now, in conclusion, we used the Reynolds number to determine the flow state of the system. We modified Bernoulli's principle to consider turbulence and losses in the system. We created time-dependent mass, volume, and pressure relations by assuming the expansion of air is adiabatic. And we created a final acceleration formula by considering gravity and air drag. We used Python to numerically solve the time-dependent equations. In our experimental setup, we created an experimental method to control the launch pressure using plastic bands. We measured the coefficient of discharge for different pressures using experimental data. And we used tracker to plot velocity and the acceleration of rockets. Here are our experimental results. I'm just going to play the video that didn't play. Sorry. Okay, it seems like we cannot play the media. Thanks for your attention.
Okay, thank you so much.